Today we'll talk about organic electronics, and the people responsible for me being able to be up here and talk about organic electronics, at least as far as our group is concerned, are shown here. And actually, I thought I would present some of Juan Po's work, but there just won't be any time. And also with Walker, I'll mention them as probably as we go on, or whatever they may have contributed to this. And also, Jean-Luc will probably have to go by the wayside because of time restrictions. We do collaborations with a whole bunch of people, including Professor Quinn Nguyen here, Alan Heeger, and Yang Yang at UCLA. And today I will present work in collaboration with all these folks here. The work is supported, and this is not working, so I'll have to go this way. It's supported by, over the years, by a whole bunch of different sources. Most recently by the MRL, where we're very grateful to have a seed IRG granted to us close to 2 years ago. And we also have support, of course, through the Center for Polymers and Organic Solids. The ONR has, over the years, been has supported the work, Air Force, and finally also a bit of work from the Mitsubishi Chemical Center for Advanced Materials. Okay, so what do some of these folks look like? There's Jean-Luc, that's West, Juan, Rajiv, and Fulvio. And then there's an old geezer someplace in the middle there. Okay, so organic semiconductors. Let's backtrack a little bit here. Let's go over here. Organic electronics. Yeah. Okay, is this better? Is this better? Can I turn it up in terms of light or in terms of sound? Acoustic. Do we have a speaker? I mean, we had a loudspeaker here, right? Oh, it's just for the video. Sorry. Maybe you can sit right here. Yeah, no, seriously. You could probably do better sitting up front. Okay. I'll try my best. Okay, so up to roughly the 1950s, if you would have used the word organic electronics, it would have been like Army intelligence, right? An oxymoron. So most engineers would have, in fact, well, yeah, that would be Army, not Navy anyway. Okay, so most engineers, up to that point, to them, organic chemistry was some kind of strange thing. You know, it has to do with maybe coal or maybe with sugar or something, but certainly not solids that would transport holes or electrons through them. And roughly 1954, Japanese workers, Akamatsu and Inukuchi, to be more precise, made the first organic material that actually conducted electricity at a reasonable mobility. And the conductivity that was recorded was on the order of about 10 to the minus 2, 10 to the minus 1 Siemens per centimeter. So pretty respectable for something that we'll talk about in a minute. Okay, so it wasn't till about the 1970s that there was some inkling that one could do something with organic semiconductors, because the fact that conductivity was discovered in molecular solids was already pretty damn exciting, and to have little crystals give that kind of conductivity clearly was quite spectacular. In fact, that paper was published in Nature at the time. Okay, so then the emphasis was on conductivity, and can one get metallic conductivity, and can one get superconductors, and so conductivity. So we did not worry about semiconductors anymore. We were interested in metallic and superconducting organics, because we knew that we could transport charge through these funny solids. And it wasn't until the 1980s that we decided as a community, thanks to a landmark piece of work by Richard Friend and his group at the Cavendish Laboratory, that in fact semiconducting properties and hence organic electronics would be in fact the future of these solids. And so that's why we're going to talk about advances in organic electronics. And it's the equivalent of saying organic semiconductors, okay? Because they're the semiconductor properties of organic materials. Okay, so in fact, it's clear that even though to this day there are people who will tell us that organic electronics is really not going to have much influence in the world. There are still folks like that. Yet we already have nice flexible displays. This happens to be a white light display, flexible because it's a polymeric organic substrate. And there already were some cell phones available with the organic light emitting diodes as part of the display. So they're here. And in fact, most of you must have seen by now the nice little display that Sony has, which is pretty expensive but spectacular to look at. And that's all based on organic light emitting diodes. Okay? Not yet one that you can take home and have 42 or whatever inches across, but that's coming. All right, so in various other fields like transistors and finally photovoltaics. And if Alan Heger were here giving this talk, he'd probably go over to his briefcase and pull out this roll and roll out a meter or a meter and a half of a fully flexible organic photovoltaic. I don't have that. I just have this picture over here where there's this little organic photovoltaic that's powering that display over there. Okay. So, and currently, pretty much what the community can do is essentially low power generation with organic photovoltaics. All right. So what I will emphasize today will be this area here and that area here, because that in fact happens to be CEM's bailiwick, right? So let's talk about okay. So organic electronic materials clearly are in a completely different universe than all engineers in this and other places are used to. They're used to working with extended solids, that is silicon, germanium, gallium arsenide, etc., etc. All these are solids made up of interconnected atoms throughout the entire monolith. We are this afternoon, we're going to be in a completely different universe. We're going to be in a place where the solid is composed of molecules. So what's the big difference? The big difference is that within the molecules, the atoms are very tightly interconnected. The interatomic distances are short. But the solid itself, the bulk, is made up of molecules that sit in a lattice that are rather far apart. And what's more, you have to coax these molecules to fall into this lattice in a particular way so that they can communicate with each other. They're not too far apart, but they are close enough to be able to delocalize or move holes or electrons through that solid. So the difference is really enormous. It's as if you let's say in a silicon semiconductor, the person that would be sitting next to her here up front would be the other silicon atom or something. Whereas in these molecular solids, there's a molecule over there, and then the next one is over where this carries. Okay, and so you're dealing with a completely different situation. Also, of course, from a structural engineering point of view, these things are soft, they're brittle. You're lucky if they form freestanding films. If you're dealing with small molecules, if you're dealing with polymers, of course, they form nice freestanding films. Okay. So when we're going to talk about the light-emitting diodes, we're going to talk about small molecules, but we can also make them made out of polymers, and we'll talk about that also in a minute. Okay, so there are tremendous advantages and also disadvantages to dealing with molecular solids. The advantages I'll tell you in a minute. The disadvantages, of course, I pointed out, and other disadvantages are we're dealing with organic solids, and quite a few engineers have a point that is organic materials that are used in organic electronics tend to get relatively easily photooxidized, so they don't like oxygen and light at the same time, and some might be sensitive to moisture, and some might be sensitive to all three of them. And because I'm an organic chemist, I'm going to say sensitive. If I were an anti-organic electronics person, I'd say they suck. All right. So let's see what the big advantages are. Okay. So I'm trying to use this. It doesn't work, unfortunately. So I might as well put it away. Okay. So the beauty is that you can design a molecule and with some kind of goal in the future. Okay? So the beauty is whatever you do to the molecule, you get in the solid. But you have to get there, right? And so to get there, you have to form an ensemble, and that's where it's only in very recent times that we've learned how to do, quote, self-assembly. And some of those rules may apply to these solids, but to this day, quite a few of them still are not available because they require little hooks and rubber bands and things that sometimes we can't put in the right place on the molecule to get them to assemble exactly the way we want it to assemble to get to the properties, okay? That is the solid-state properties that we're interested in. Okay. But the beauty is, and you'll see a lot of that, so that you'll get bored by the time you get all these design features here. So we can, by looking at what we want out here, we can go back and have this feedback loop here where we can see, okay, well, we need something else to do here. We need to change the electronic gap. So then we go back and we redesign the molecule. And the beauty is that the ensemble reflects exactly the molecule. That's the beauty here. So inorganic solid-state guys don't have this. Okay, they have atoms, and they can put atoms in, they can take some atoms out, and they can arrange the combinations of atoms, and Ram is sitting there and say, well, Fred's full of crap. But in fact, I do have a fair bit of information there. Okay, so let's see then what we can do with these. If we want metals, yes. Can we make superconductors, as I mentioned before? Yes. In fact, it was very interesting. The highest TC of an organic superconductor, if you can consider fullerenes organic, we could argue about that, is 40 degrees Kelvin. Now, this happened about a couple of years after the high TCs. It would have been about 2 years before, they would have seen the high TC superconductors. Well, and there are lots of other things we can do. Of course, today we're going to talk about semiconductors, and of course we can make lots of them. And finally, there are lots of other solid-state effects that one can use. Ferromagnets, to this day, the transition temperature is rather low. It's not surprising because we're dealing with molecular solids, and the spin-spin interaction is going to be really, really weak. Okay, so as a result, these things have transition temperatures in the order of 12 to maybe 20 degrees Kelvin. Okay, so if you want a very cold magnet, you can make an organic magnet. And however, in the case of ferroelectrics, we got the inorganic guys beat. Okay, with polyvinyl fluoride, PVDF2, we can make these tiny little microphones that everybody that has an iPod or whatever uses are due to these very, very good ferroelectric polymers, and nonlinear optics and so on. All the other, in other words, all the solid state properties that are associated with inorganic inorganic semiconductors can now be done with organic molecular solids. Okay, so we're going to talk about semiconductors. And so one of the main driving forces, as we all know, and we have a big center here for lighting, is to make white light that is not going to require incandescent or fluorescent lamps. And those are going to be based on light-emitting diodes. And of course, the organic guys are way there, and they're way ahead of you guys, inorganic guys, in some respects. So here's a case that I'm going to describe in some detail. It was published together with Yang a few years ago, and then a much more efficient system was put out by these folks here. In fact, I just saw this guy sitting in the audience over here, and we'll discuss the difference between those two. And of course, these are organic, right? And you can see this white light is a little nicer white than this white over here, which has a little blue tinge to it, right? So, and they're very, very bright. We're going to see the brightness. I mean, the candelas ramp. Okay, so how about photovoltaics, you guys? All right, organic. And here's a paper that was published a couple of years ago by Alan's group together with a few other folks. And of course, they did a tandem cell, and they managed to essentially double the efficiency of in those days, the photovoltaics. Yang claimed a few weeks ago, and claims it's coming out in the literature, that it can do close to 7% efficiency without having to make a tandem cell. Okay, so the goal for all of us working in organics is to get 10% power conversion efficiency. Once we're there, some of the engineers will talk to us, and they'll make things out of them. Okay, so 10 is the current goal for organic photovoltaics. Just to put things in perspective, the first organic photovoltaics of the current generation, that is the ones that we call bulk heterojunction devices, were discovered here in the early 1990s. And the efficiency in those days was less than 1%. And for quite a while, we were stuck at about 2%. And then we learned all kinds of tricks. And again, we designed the system, we modify it, and we get better and better. And so 10% is not nearly as far away now as it looked 2 years ago, let's say. Okay? So we are definitely, and I'm very optimistic that it'll happen. Okay, so those are two areas that we're going to talk about today. So to be able to talk about them, let's divide into two large families. Okay, organic semiconductors can belong to either polymers or what we call small molecules, and both of them have their advantages and disadvantages. From a practical or technological point of view, clearly polymers appear to be more attractive because they form films readily, freestanding films, and can be dealt with in more familiar terms to traditional engineering. On the other hand, the small molecule systems are also manageable in more familiar terms in the sense that they can be vapor deposited, and we know lots about vapor deposition in terms of current semiconductor technology. Okay, so those are the two big families, and of course one can make all these things within each one of the families. Now, if we look at the parameters, the ones that we can design and modify and so on, okay? And the important ones are actually the highest occupied molecular orbital and the lowest unoccupied molecular orbital, and of course the gap between them. And for if these were actually extended solids, then the HOMO would be the valence band, and the LUMO would be the conduction band if they were to form bands. And of course, the nature of the charge carrier, holes or electrons, for the longest time, the hole generators were, or hole conductors were really very easy to come by. In fact, still are. N-type semiconductors are a little more difficult. There are now quite a few of them available to us. Mobility is, in some cases, still a problem, although we can now with organic molecular solids, small molecule pentafene, we can do just as well as amorphous silicon, if not better. And finally, and I always leave this for the end, but this turns out to be the most important beast over which we have very little control. And all this is, of course, empirical, but we have quite a bit of theory behind this, but there's practically nothing behind this. Okay, this is all seat of the pants, and it's all really empirical. And you'll see, I'll show you a table in a few slides of what it really means, this processing bit. Okay, so let's talk about light emitting diodes, and let's talk about two important aspects. One is to make a stable blue light emitting species, and of course the goal is to make a high efficiency white light. And I showed you in the third slide or so a white light emitter. Why do we worry so much about blue? Blue is the highest energy emitter in the spectrum. So we can use the energy that it emits, the blue light, to pump the other colors. So we use blue to generate red and green. Okay, and so that's why blue is so important. Also blue, because it's a high energy emitter, is very difficult to make very stable. Okay? And so because, as I mentioned before, some of these organic molecules really like to commit suicide. And so by giving them that much energy, you're getting them closer to committing that. All right, so we're going to talk first about at least our contribution to blue light emission, and then we're going to use that to make white light. All right, so this happens to be a hydrocarbon, which has been in the literature for a long, long time. And Brian Kecky in the group a few years ago decided to look at its properties. It turned out to be quite a nice hit. So here's a molecule that was designed to be a blue emitter, and look at this luminescence, or luminance. You compare that to a CRT TV. Some of you who are very young may not even know what a CRT TV is. But a CRT TV is about 200 candelas. Okay, so you can see how incredibly bright this thing is, and the efficiency is rather good. Although nowadays we talk about 15 candelas per amp in terms of efficiency. These are the people who did that. There was another group who also made a rather large molecule, not as luminescent, also not as efficient, but anyway, they published about 2 years after this group. And then finally appears what Brian Kecky did. And the reason we have this here, this is a multi-step synthesis, which requires a lot of work to build. This is a multi-step synthesis. This is what I would almost call, if it were a one-step, I would call it a physicist synthesis. But so we'll call it engineering synthesis, because it takes 2 steps. And by the way, it's not surprising that the more synthetic steps it takes, the less of the material you're going to get, a lot less of the material you're going to get. And if you can only get a few milligrams, ain't nobody going to talk to you, all right? So you have to be able to make hundreds of grams, if not kilos. And so when you do something like this, and that's very attractive because both steps are high yielding and easily accessible. And just to tell you how empirical things still are, okay? This is a blue emitter and has a rather high quantum efficiency. If you put another channel over here, it's dead. Oh, that was done a long time ago in the early 1900s, and it's been known that if you have tri-channel fluorantine, this fluorantine is the basic unit over here, which comes from tar. Okay. Most of these compounds come from oil tar anyway. Yeah, right. Just empirical. Okay, so just to tell you that, okay, you put another channel over here, bam, no fluorescence. You remove this channel, you get fluorescence, but different color, not as efficient. Okay, so the only rule of thumb that we have for a molecule to be a relatively efficient fluorescer is that it should be a very rigid system. Okay? Not allowed to diffuse its energy into vibrations and other modes, so that the efficiency, the conversion to photons is the most efficient process. Okay, so once we had this, then we connected with Yang and made the devices. So here's the spectrum for that compound. So here's the absorption and the fluorescence, and we put it in PMMA and showed that it fluoresces just as well. And molecule also phosphoresces. Now, quite a few organic molecules do phosphorese. Unfortunately, they do it at very low temperature. Okay, 77 K. On the other hand, inorganic, that is, inorganic or organometallic compounds tend to phosphorese at room temperature and quite efficiently. And in fact, people, most notably Mark Thompson from USC, have taken advantage of that and have made very, very highly efficient light-emitting devices that way, molecular light-emitting devices. You can't call them organic anymore, right? Because now they have the principal thing is an iridium or a platinum or some other very heavy electron-containing element. Okay, but this is a nice, efficient and relatively narrow for an organic molecule. Now, on the other hand, the organometallic phosphorescers are very sharp. Nice sharp emitters. Okay. So there's the blue color, and so now. This is sort of a cartoon version of what happens and why once you know the fluorescence, once you know that a molecule is going to fluoresce, you know it's going to electroluminesce, because the process is essentially identical. So you have a molecule that has the highest occupied molecular orbital, which is filled, an empty lowest unoccupied molecular orbital. You hit it with a photon, bam, you excite one of these to an excited state molecule. Now, this electron can fall down to the ground state, has to give off a photon, gives you back the ground state. By the way, the color of this is different from the color of that, and we can talk about that later. There's no time for that. Okay, now let's look at electroluminescence. So this would be photoluminescence. Electroluminescence, well, you apply an electric field, and you can generate a hole and an electron. So the hole is here, the electron is there. And now when the electron recombines with the hole, bam, you get the molecule back, and you get light again. Okay, so you've generated this state using an electric field. You've generated that state using a photon. But the gap being the same, you get exactly the same color. This light is the same as that light, and you will see that in a few slides for the rest of the talk. Okay, so that's in principle how things are supposed to work. So let's look at a cartoon of a device. So in this case, we have some kind of metal, usually a low work function metal. We have a transparent cathode. 99.9% of the time it's indium tin oxide glass, although you can get plastic with indium tin oxide on it, and that's how you make these flexible devices. And then you put your emissive layer between the two. This is by far the simplest and usually doesn't work device. So we'll show you how this works. So by the way, this is the way an electrical engineer would draw this. If you were a chemist, you would say, okay, I don't holes are just absence of electrons. So what I do is I have something here which is going to suck electrons away, a power supply, and it's going to dump them back in here. So we close the circuit, and so then we have, in a battery sense, this would be the cathode and this would be the anode. But we're talking about engineers here, so they got things screwed up. Anyway, so you have a low work function metal, so there's a source of electrons, and you do a power supply, you have a source of holes, or you remove electrons. Okay, so what happens is, so it creates holes in electrons, and they travel through the medium. And what if, instead of them recombining in the middle someplace, they get near this edge over here? A couple of things can happen. The first thing that will happen is that this particular semiconductor will probably quench the luminescence, and you won't see any light. Okay. So then what you have to do is you have to put a hole transporting layer on this thing to separate the active species, excitons, from the actual surface of the material. Okay. So now the holes can travel, can be closer to here, but maybe they travel too far and they ended up at this other electrode. So in that case, yeah, you get light, but it's not the light that you want. It'll probably be a different color because of other effects. So now we have to put some other layer in there. And so we put an electron transporting layer or a hole blocking layer, same idea. And now you're forcing the holes in the electrons to recombine in the middle. And guess what? You get the color that you were supposed to, which is blue. Okay? So that's it. So that's a cartoon. It's a nice, cute cartoon. In real life, this is what the device ended up looking like. All right? So, first of all, for those of you in the audience who are electrical engineers, really nice semiconductor device. On-off ratio, rectification ratio, close to 10 to the 10. Very nice. And for those of you who are into light-emitting diodes, that's a pretty respectable brightness. Okay. All right. Now, here's our PDOT. IPO. You'll see the structure of PDOT in a minute. Again, this is also for hole transporting help. This is that red thing that I drew before in the previous slide. This is also part of the red thing. It's not empirical. It turned out that this wasn't good enough. We needed a second layer. Here's our blue emitter. Here's the electron transporting or hole blocking layer. And finally, we have a low work function alloy of calcium and aluminum. And so just so you know that I'm not trying to confuse you with all kinds of alphabet soup, I will give you the structures of these things. So the usual hole transporting layers, and for those of you who are organic chemists, that means these are relatively easily oxidized or generate holes rather readily. Why? Because they're phenylenediamines. And this is PTB, that's MTB. And finally, this is a more electronegative molecule, and as a result, it'll be willing to produce radical anions if you force them. So these will be the electron transporters, and these will be the hole injector and hole transporting layers. Okay. So now, just to show you that in fact fluorescence and electroluminescence really track each other. So in the dark squares is the fluorescence, and in the open circles is the electroluminescence. Pretty much identical. There's a little change over here, but essentially the same. And the efficiency lasts a long time, provided you leave these devices inside a glove box. If you take them out, good luck, because they're sensitive to oxygen and moisture and so on. So what people do, of course, they encapsulate them usually in epoxy, and that makes them live for considerably longer time. In fact, quite respectable time. Okay, so about the same time when we were doing this, a lot of other people started making even much more efficient devices. These have only 3 candela per amp, but there are now devices based on phosphorescence that go up to 10, 15 candela per amp, and they're really considerably better than this. But this turned out to be, for the time, a very good one. Okay. So now that we can do blue, let's make white light. And as I said, to make white light, you need something that will give you red and green. And that's the other beauty of organic molecules, is that they have a very broad absorption and very broad fluorescence. You can make them have broad fluorescence. And so, and here again, another thing that happens a lot with organic chemistry and organic electronics is serendipity. So we were not out to design a molecule that had this very broad emission that was both in the red and the green. It just happened because we were working on another large family of interesting molecules, the so-called linear oligosins. And now, I apologize, that's in my computer, that's not yellow. This is getting old. Maybe it's time to replace that because green is not coming out too good. Anyway, so here's the smallest acene. It's not called an acene, it's benzene, naphthalene, and the smallest acene really is anthracene. And for the longest time, these were all obtained from coal tar, and a lot of organic dye chemistry is based on all these guys. And a lot of pharmaceutical stuff is based on benzene. The higher members are much rarer and rarer to the point where heptacene doesn't exist. It is incredibly unstable. It polymerizes. It commits suicide the minute it sees the light of day. Okay, doesn't even see the light of day. So what we, as synthetic chemists, we all know that we can force molecules to survive if we decorate them with all kinds of things so that they won't see each other. I mean, they won't see a neighbor, and that they will do other things to prevent them from self-destructing. And so what we decided to do with Xu Dong, whose name didn't appear in the first slide, is to just really decorate the whole molecule in such a way that it'll survive. And so what he made was this, what we call TBH. And so here's the heptacene part. But you can see we have 2 aromatic rings flanking them. Now this looks more like a pyrene. And then we've got additional 4 phenyl rings. And guess what? Some of you who are organic chemists already realize that this is not the truth. The truth is that these guys occupy a lot of space. And there are hydrogens here. And there are hydrogens there and there. So what happens, you get a really badly twisted molecule. Even though these are all sp2 hybridized carbons, so that means they have to be coplanar. But they can't. Okay, so they really get twisted. And there's a crystal structure right here that shows you just how badly twisted these things are. So this guy is, let's say, that guy over here, and that little bit that you see back there is this guy back here. So this whole backbone here is just really nicely twisted, almost like a propeller. Okay? And so because it's so twisted, that finally, in the last 2 years or so, 3 years, 2 groups, John Anthony in Kentucky and Doris Chung in our group, have made a real heptacene, and heptacene is actually green. But this molecule overall looks red, but it does emit over a large area. Here's the electronic spectrum. So here's the absorption. So if we had a blue emitter, it would be able to pump this very nicely because blue light is right there. That's the absorption, and here's the emission. And look how far the emission goes. It goes all the way from about 500 to around 730 or so. So it covers the red and the green. Okay, so if we were to combine this with a blue emitter, which happens to be a polyfluorine, and so here's the blue emitter, and now you keep adding little bits of that PS, dope it into that blue emitter, and if you dope as little as 5%, you end up with white photoluminescence. It turned out that for electroluminescence, you required a lot less. Okay, and so here's the only reason I brought this up is because I want to thank Mr. Bill, as in Bill Gates, because if you look over here, there are no numbers, they disappeared. There are no numbers over here. This is sort of screwed up there. Anyway, so I had to go back to the publication and get the picture out of the publication. It's not as pretty, it's not as colorful, but at least it has numbers and you can see what you have. Okay, so this device again, it's only about 3.5 candelas per amp. This is when we published this around 2004, 2006, and about the same time, Alan Heeger and Guy Bazin used a phosphorescor, a red phosphorescor dopant, to get 5-point-something candelas per amp. So they beat us in that. But we got a nice white light. Anyway, so the turn-on voltage is quite respectable. Barely at 2-3 volts it turns on, and then it just really, if you get to 8 volts, you're way up there in terms of brightness. And in fact, that's the picture that I showed you about slide number 3. And here you can see that it only took 1% of the TVH to get the white light that we wanted. The other beauty of this is that if you can also get green light if you put very little of this material in there, and you can actually dial in the color light that you get out, depending on how much material you dope into the polychloride. Okay, so here's a summary then, and you've seen this before. So that's the bright white light, and then we'll talk about that in a second. And that's, well, I didn't have Alan's reference. It's the same year, 2004, in advanced materials. Okay, this tells you just how close you've gotten to white light. Okay, there's an international convention that is shown over here to give you the main colors, the red, blue, and green. And if you are at exactly 0.33, you're right at the sweet spot of white light. We are at 0.32 and 0.32 over here and 0.36, so we're right about there. Not bad. Okay. So the most recent that I've seen was this year, where they got 3.2 and 3.4 for the X and Y coordinates. So we're essentially there for really good white light production. All right, so let's now quickly go to photovoltaics. And the reason, of course, is that last year's Nobel laureate and Peace Nobel laureate told us that we should do that. And there's something wrong with this statement up here, right? What is it? It is a political issue. Okay. You can't get away from the fact that it is a political issue, and will be a political issue for a long time. All right. Fortunately for us is that in molecular solids and also in inorganic solids, the two systems of photovoltaics and a light-emitting diode are essentially the microscopic reverse of each other, right? So this happens to be another light emitter that happens to be polymeric instead of small molecule that we've been talking about so far. And if you apply charge, you get light, and if you supply light, you should get charge. But yes, that works, but it's not very efficient, rather inefficient. So you have to modify the concept a little bit. And so this is the concept that evolved here in the early 1990s, where we're talking about the bulk heterojunction cell, where you provide light and you get electricity. And so we're going to spend the rest of the, hour or so to talk about that, right? John shakes his head. It's not going to be an hour, hopefully. Okay, so what are the electronic processes? So we go back to our little cartoon. We start with our molecule here. We provide light. We separate the hole from the electron. And so we have the hole and the electron. And guess what? If we can get this guy to go to one electrode and the hole to go to the other electrode, then in principle we can get electricity out. On the other hand, you can get exactly the same place right as we said before, just from the fluorescence work that we had in the previous cartoon. So we want to go this way and end up over here. Now, no, this happens to be an error. It could be a triplet if you had a phosphorescent, but it's a single. So thank you very much. The audience is awake, at least one member of the audience, and realized that I drew a triplet excited state here, and that would be for phosphorescence, but not for not for what we want to do here. Okay. All right. So there's a very nice website that I suggest most people go to. It's due to Sadar Tifchi, in fact, one of the protagonists of discovering the Volkswagen junction cell here. And here's a typical picture of a flexible organic photo cell. And here are the ingredients, and we're going to get back to that in a little while. And these cartoons are completely wrong. This one is right. This one is way over too oversimplified. We're going to get to that in a minute. And so there's a better view of the protagonist. This happens to be a fullerene derivative that was designed and synthesized by Kees Hommelen when he was in our group here in the early 1990s. And this happens to be a polymer that's used by Tifchi and others because they don't want to interfere with our patent on MEH-PPV. So anyway, so that's an MEH analog. But it's still in violation of the patent. Because the patent says any branch chain would do. All right, so these are the two characters. Let's look at another, a little better cartoon here, also from the same group. Again, this one is way oversimplified. If this were a piece of the device, then all this is filled with this spaghetti. The spaghetti happens to be the conjugated polymer. And then within that spaghetti, there's another filamentous spaghetti within that is made up of the fullerene derivative, of the PCBM. And so they can really get close to each other and communicate so electrons can hop from one ball to the other. So what happens? The photon comes in, and the electron gets transferred from the conjugated polymer to the fullerene derivative. A hole remains behind. The hole diffuses to one electrode. The electron hops from ball to ball, goes to the other electrode, and now you have created two charges, and so you have essentially electricity. It ain't as simple as that, but that's the cartoon picture. Okay. Now it turns out, as I showed you with the light-emitting devices, life gets a lot more complicated. All right. So for one thing, what are the challenges? A lot of challenges. Still to this day, to make a device with a high charge carrier mobility, the fullerenes do that okay, about 10 to the minus 2, 10 to the minus 3 if you're lucky, centimeters squared per volt second. The conjugated polymers don't do nearly as well. That is the P semiconductor. And here we are again with the processing and morphology. And in all these devices, whether they're light emitting or whether they're to produce electricity, processing and morphology are key for improving the efficiency. So this happens to be a list of conjugated polymers that are still the most studied. Not all of them. This is not studied that much anymore. This not at all. Not at all. And this is still to some degree studied. This is the oldest of the bunch, polyaniline. Okay, so these are mostly for making blue light and also for making all kinds of interesting devices in the Bazan and Quinn group, and Nguyen group. These are the ones that were first used for both light emitting diodes and also photovoltaics. Now, the reason these were so interesting is because you have at least 3 different sites that you can play with to modify all the properties that you wanted to modify. And by contrast, the polyfluorenes, you can only really play with these two guys. And all they do is help you in terms of solubility or making polyelectrolytes or varying those kinds of things, but or varying the solid state structure. Electronically, you can't do much. Okay? Here, electronically, you can do a fair bit. But by far, the ones that are used by far the most are polymers based on these molecules here, where X is sulfur and Y is some kind of organic long chain. Okay, so and then here's our friend P dot that we always use as a first layer on top of the indium tin oxide. All right. So now, just a little lesson in stereochemistry of polymers. The first poly-3-hexylthiophene that came on the scene was just called plain PCHC because we had no control over where these R groups were in the chain. So this is a regio-random polymer. This happens to be a head-to-tail regio-regular. That's what the two little R's are. For those of you who have worked with this and don't know what the little R's are, this is what the little R's are. It's regio-regular. That means they're in the same region in space as you propagate the polymer. You can also have a different kind, which we don't study at all, which could probably be the same, if not maybe even better. A head-to-head, tail-to-tail, regio-regular poly-3-hexylthiophene. So this is it. So we can highlight it, and we're going to the rest of the talk is essentially based on that. But okay, so this is a relatively simple-looking system, and contrast that to what has happened in the much more recent past. This goes back all the way to the 1980s. Okay. This is 2006. So look how, here's our friend, the polythiophene, but now it's combined with another carbon here, and it's got these solubilizing groups, and then we have this other group here, and it influences the electronic character, that is the electronic gap of the system, because now this is a more electronegative molecule, this is a little more electropositive, so you can have some kind of intramolecular donor-acceptor interaction, which affects the size of the gap. So you can see again that third slide or second slide that I have. Design, a lot of design goes into this to get the solid state properties that we ultimately want. Here's our old friend, the modified C60 PCBM. And it turns out C70 PCBM gives higher efficiencies only, very simply, because it absorbs more in the visible. That's it. Okay? C60 has very little absorption in the visible, even though it's purple. It's purple because there's a tiny little absorption in the visible, but our eye detects that. Okay. Whereas the 70 PCBM has a stronger absorption in the visible region. So these are the ones that, in fact, are currently, particularly polymers based on various combinations of these two, are the current thing. All right, so most of you in the audience know what the parameters are for getting the efficiency of a solar cell. It's the current, the open circuit voltage, and a fill factor. And we'll talk about this in a second. In fact, what does it look like? What does the experiment look like? Here's the solar cell based on the previous polymer that I showed you, mostly done by Babic a 3 years ago. The ideal solar cell, and some of these, see, that's where the silicon guys are way ahead of us. The really good solar cells, they look almost like a square, like that. Okay. So here's when you have zero current, that's the open circuit voltage, and when you have zero voltage, this is your short circuit current. And so you want to maximize these two, but if you were to maximize them too much, you sort of get this gets lower and shallower, and in fact the fill factor is whatever is in here. So if it's perfectly square, then you get the maximum fill factor. Well, the difference between the maximum and what you see is actually the fill factor, and that tends to bring the efficiency down, of course, and unfortunately appears in the numerator of the equation. So if it comes out as a small fraction, you really suffer. And we'll show you, in fact, how this can really affect the system. The other, of course, and these are another key design parameters. And again, some things are empirical and some things we know how to control. What we're given is the Homo and the LUMO of PCBM. And would you believe to this day, there is still an argument as to what that number is. Okay? Some people say minus 4.1. Why minus? Well, vacuum is up here someplace, and we're doing this relative to vacuum. Okay. So minus 4.1. Other people say minus 4.3. There are, in fact, some people who say 3.9. So let's say Brabitz is right, and let's say it's minus 4.1. So why is that important? Because the open circuit voltage, that is the volts that you can get out of this battery, solar battery, is the difference in energy between the HOMO of the donor, in this case this polymer, this alphabet soup polymer, and the LUMO of the PCBM. The smaller this gap, the smaller the voltage that you can get out of the cell. This difference is the driving force for the cell. So the closer these two get, the less of a driving force you have. And if this happens to fall below, of course, then there ain't going to be no photovoltaic device. All right. So the idea then is that all of us in the field have been working with, we're given, this is a given, okay? And so we say, all right, we got this, we're stuck with it, and we'll talk about that. Well, I started late because I had trouble with my Mac, right? And then you introduced and did all kinds. Okay. Anyway, so we'd like to make this gap smaller so that we can absorb more of the visible range. Well, if we make it smaller, we're going to probably lose in terms of driving force. Or the best thing that we could do is take this whole thing and just move it down. Just take that and just move it down. Okay? So if we can put the HOMO down here, then we get that much more open circuit voltage. And we can still bring this down a little more. And so that's what essentially all of us who work in this area are trying to do. And we have some ideas how to stabilize the HOMO, and we have some ideas on how to stabilize the LUMO. And so one of the ideas is you saw in the previous polymer, by making this bithiopene with a carbon between them, we've lowered the HOMO a little bit. By putting that electron acceptor, we monkeyed with the LUMO, and so that's why that combination exists. Okay? And then we can also play a little bit with the injecting metal, and John Gong and Alan have recently done a very nice piece of work, which I will refer to in a second, about how the influence of that on the efficiency. Okay. So here's something to show you how empirical and how ugly the field actually is. Okay? So here's a big table, and I expect you to see everything on it. No. But I'll emphasize something. Here's the efficiency. And so these are all based on poly-3-hexylthiophene, regular, and depending, there are changes in molecular weight, over which sometimes we have control, and most of the time we don't. Then we can play with the ratio of the PCBM to the conjugated polymer, layer thickness, and here is the processing. This stuff has to do with processing. Okay? And what's missing here, you can also use a tiny bit of a co-solvent, right? That was discovered at Santa Barbara a couple of years ago. And that will tend to allow the fullerene derivative to coagulate a little better, and the conjugated polymer to crystallize a little better, and so you get a little more order, and as a result you might get better efficiency. Look at the whole map of efficiency. They can range anywhere from 2.7 to 5 power conversion efficiencies, okay? And these are all the various references of different people who work on it. The problem is, it's so much work, and yet, let's suppose you wanted to generate this in your own group, right? Just to know just how good P3HT can get. So we don't know just how good even a simple system of P3HT. And every time we design a new polymer, we have to go through pretty much the same game to improve on the efficiency and to get this stuff out. Okay, so by playing sort of this game, Yang has gotten close to 7, and so this is a record for Babbage for this year, based simply on PCHD. Oh no, based simply on PCHD. Okay, so we're coming close to the bitter end here. So now let's talk about the fullerene. Okay, so we can play all kinds of games, but very few games. We can't change that much. Yeah, we can go to 70, and that's about it. We can play with this atom, and here we have Jang-Duk has done that. He's changed the carbon to nitrogen. In principle, you've gone from a less electronegative to a more electronegative element. That should make this a better acceptor, which unfortunately what that means, it lowers the LUMO a little bit, so it makes the gap a little less. That means your open circuit voltage will be lower. And that's in fact what was found. But the solar cells that were made had very nice fill factor. So you can see this. This is coming much closer to a square, right? So this happens to be PCBM, and this happens to be one of the nitrogen-containing systems. It tracks PCBM pretty close, but the open circuit voltage is a little less than PCBM, which is due to the fact that we lowered the LUMO a little bit. Okay, so now the problem is there ain't much you can do with fullerene. Why? The only thing you can do is add things to it. You can't substitute. Yes, you can. We substituted a long time ago a carbon for a nitrogen here, but then you put in a trivalent element that makes an open cell molecule. That's a problem. Okay. Why is PCBM, or why are fullerene derivatives so good? So we have to backtrack a little bit, and I am coming to the end of this. So before the fullerenes came along, people really worked hard at getting organic solar cells to go. The main problem was, remember, in the case of these cells here, polymer absorbs a photon, transfers an electron to the P60 derivative, to the PCBM. That step is reversible. And in all systems before fullerenes came along, the back step, that is the back charge step, was as fast as the forward. In some cases, even faster. So you got nothing, you got zero. Okay? Fortunately, in the case of fullerenes, the forward step is between 1,000 and 10,000 times faster than the back step. One hand-waving argument that's reasonable is that fullerene is highly strained because you're forcing sp2 hybridized carbons to bend. Okay? You add an electron, you expand it a little bit. And the site where you added the electron becomes sp3 hybridized. So that relieves quite a bit of strain. It ain't going to want to do this again. So it's just going to be relatively happy, and it's just going to transfer from one molecule to the other, from one PCBM to the other. On the other hand, all the other organic receptors that were tried, and we have lots of, we have a whole armamentarium of them over the 100 years that we've been doing business. None of them do that because they're pretty happy they're pretty happy one way or the other, so they'll just give that electron back again. Now, there's another way to introduce strain, and that's by doing an angle strain and combined with a steric strain. So what we have here is two hydrogens that are really running into each other, so they're trying to force this molecule away from planarity, but it wants to be planar because it has two sp2 hybridized carbons in the middle. If we add an electron to this section right here, then the thing can twist very nicely. It relieves the strain. Plus, it becomes very stable as an anion because there's a famous chemical physicist, physical chemist by the name of Wudl in the United States, who calculated many years ago that whenever you have 4n plus 2 pi electrons, you have added stability. So there's a driving force to produce this radical anion. So it ain't going to want to go back that way. The beauty of this system is that you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 places where you can play all kinds of games. Okay, and this is where Fulvio comes into the picture, and he makes a whole bunch of these. All right? And this isn't all. But it turns out that of all of these, this turned out to be the most interesting one. And if we look at the Homo, at the LUMO, you can see it's considerably higher than PCBM. So in principle, this should give us a much higher open circuit voltage, which it does. So we've managed, in fact, to do that. But before we go there, the first thing that one has to test is to see if, in fact, this acceptor will take an electron from a photoexcited donor. And it does a beautiful job because it really quenches the luminescence. Here's the luminescence of PCHD. You add some of this stuff to it, and bam, the luminescence is gone. So it just robbed that electron away so it couldn't fall back on the ground to the ground state. Okay. So here's pretty ugly. John, I apologize. I call it ugly. Okay. Photovoltaic device. But if you look at the open circuit voltage, it's close to 1.3 volts for this particular cell. The better looking cell, it's still considerably higher than PCBM. So what we, of all of us working together, what we got out of that is, oops, that's wrong. We got a doubling of the open circuit voltage of organic photovoltaics. So in principle, that should give us double the efficiency. In practice, no. We got, well, something like 2%. Why? Because the fill factor, you can see the fill factor really, to use the vernacular once again, really sucks. I mean, this is, okay, it's pretty bad, especially in this case here. That means that the short circuit current is very poor, and we know that. And we know that because these molecules, the 9BFs, do not like to interact with each other. So what Fulvio is doing, so here we go back to design. What Fulvio is doing, he's playing with making these much larger pi surfaces, and there are other members in the group who are also working on doing various other tricks, adding sulfurs and for stronger sulfur-sulfur interaction, so that we get better electron hopping from acceptor to acceptor. Anyway, I've run out of time. Thank you for your attention.
Thank you, Fred. That was wonderful. Before we take questions, I want to make one announcement I should have done earlier. But Dave Austin